The last four problems for the mini exam from, well, it was called mini exam 4, but the last four problems are what's due today, and it's going to be mini exam 5 is what we're going to call that. Make sure you've turned it in. Make sure your name is on it. Name. Thank you. Bring enough to share. All right. We finished class last time. Well, I will mention I have been asked about how many more mini exams should we expect, right? Probably one or two more. You know, we'll see. The syllabus says you'll have anywhere between 5 to 8. So we officially have 5 now. So maybe another 2, 3. I'm not going to go over 8 though. And I don't have the one for you today, so maybe next class, maybe next week. I'm not in a hurry to give you a bunch of work, and I'm not in a hurry to have to grade a bunch of work right now. So just hang tight. I'll let you know when I've got it for you. When we finished class, we were talking about. I forgot my setup today, my tripod and everything. I forgot it at home, so I'm just going to sit here and see how this works. And I'm going to turn my chair because I get kind of nauseous doing this all class. So I'm just going to turn like this and see how this works out. All right. You remember we were doing double integrals? And we had talked about integrating over a rectangle was the easiest way to integrate. And then we had this thing called a type 1 region. And a type 1 region you have in your notes is where your x is bounded between two constants and your y is bounded between two functions of x. We are in 12.2, yes. So we did example 1, right? And I don't think I finished the computation, did I? No, I left that integral. I said you can figure that out yourself. And now we're going to do example 2. So that's where I'm picking up today. I need to be in day 15. There we go. Okay, so for example 2, 12.2, example 2, we have find the volume under z equals x squared plus y squared on the region bounded by y equals 2x and y equals x squared. Now, I'm going to bring the picture of this up, and you've got it in your notes, what it looks like. But again, let's act like we don't have that picture. And let's figure out how we're going to, figure this out. So I like to draw the domain first. If possible, draw the domain. And let me start out with y equals 2x. That's a line, right? Passes through the origin. If I plug in 1, I get 2. If I plug in 2, I get 4. So I've got this line, looks like this. So yes, I would expect you to be able to graph a line, in this class. And then y equals x squared, right? So y equals x squared is going to look like what goes through the origin again, right? 0, 0. I plug in 1, I get 1. I plug in 2, I get 4. They happen to hit right there. But the parabola also goes the other direction like this. So if I'm decent at graphing, I can already tell the region. It's the region enclosed by these two graphs. So it's this right in here. Right in there. Not only can I tell from my picture the region enclosed, I can tell that I have a function on top which is the line, and a function on the bottom, so to speak. So I have an upper limit and a lower limit is in terms of my y values. My y is trapped between those two functions. My x is trapped between two constants. Agreed? So let me label some stuff here. I'll label the red one. Well, the red one's going to be the one on top, right? So you'll see this might add a little value to what we're doing here. Sometimes it's better to come over here and just kind of exaggerate what you have, like this. You do this usually a lot more in Cal 1. Your y value is stuck between here, right? Your x values are stuck between two things. So the top function we'll call g2 of x, and that was the line, right? So 2x. And the one on the bottom was g1 of x, and that's the x squared. Agreed? What's the restriction on x? 0 to 2, right? 0 to 2. So I'm just labeling those over here. And we said in class last time, if you couldn't do it with the picture, if you had to figure out where these two hit each other, you would just set them equal to each other, right? So you would just take the 2x, set it equal to x squared, right? Like that, if I wanted to find the points. And from what I saw from a lot of you that came in for help on the Lagrange problems, you divide both sides by x, right? No. You move everything over to one side of the equation, all right? I have to stress that again because I keep on seeing it being done incorrectly. If you divide by x here, you're eliminating solutions. Move everything over to one side, then factor. So x minus 2 equals 0, and you get two solutions. They are 0 and 2, and that matches up with this here, right? I would suspect that on a take-home mini-exam problem, the two functions, when you try and figure out where they hit each other, is going to be a little bit harder than that, right? You would imagine that the take-home, it would be something more complicated, probably even a little bit worse than even perhaps a quadratic equation, right? Might be cubic, might require synthetic division. Who knows, right? Who knows what that crazy ass is going to give us, right? Or it could just be this. Who knows? On a test in class, of course, I would give you something like this, and you just grind it out. We'll see what happens. So let's talk about the integrals. The integrals for a type 1 region should be double integral. The first integral, the limits are the restriction on x, which would be what for us? 0 to 2. The restriction on y, which would be, you start with the bottom one first. When I say bottom, what do I mean? If you say top is higher than bottom, right, like this, what if this region was, what if we had that same thing but it was down here like this, below the x-axis? Which would be the top, which would be the bottom? It's the same thing, okay? We're going to treat it the same, top and bottom, okay? So the red would be top, green would be bottom. Remember that if you ever get that order wrong, top and bottom, how is it going to affect your answer? Just a sign, a negative instead. So the bottom one is the parabola, so x squared. Top one is 2x. And now what is it that I'm actually finding the, like what's the function inside here? X squared plus y squared. D what? D what? dy dx. Okay, so remember that the x squared plus y squared, that was the surface, right, above this region, and then the integral below that, or the area volume under that, is going to be this integral, right? Okay, shall we integrate? Last time in class, didn't I split it up and I did, let's do the inner integral and then we'll come back? Today, what I'm going to do is the way I normally do it. I'm going to keep it all together in one line. So I'm going to, just so you can see both ways. Okay, here's my inner integral. And then out here I put my dx. See that? So it's the outer integral is still there. What happens to the inside? So what is the antiderivative of x squared plus y squared with respect to y? You get x squared y plus 1/3 y cubed, evaluated where? Between x squared and 2x. But what are we going to replace? The y. So y is going to be replaced with x squared, and y is going to be replaced with 2x. So that's where I was telling you again, it's useful sometimes to keep track of the variable here, which equals integral 0 to 2. Okay, let's plug in 2x for y. What do you get when you plug in 2x for y? 2x cubed plus 1/3, no. So I plugged in for that y, I plugged in 2x, and that gave me this. Now I plug in 2x to this. 2x cubed is 8x cubed, but then 1/3 of that. So I get 8/3 x cubed. Agreed? And then minus, now let's plug in x squared. So you get what? X to the 4th plus 1/3 x to the 6th. You multiply exponents, right? All of that dx. And this is just a polynomial, isn't it? So you could just maybe, well, do we have any like terms? Yes, we have some like terms here. And we can put things together, and then this is just a Cal 1 problem, right? So I'm just going to say dot, 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 meaning you could finish that out. I think the part of this that's Cal 3 has already been done, right? Okay. Questions? Do we care to see the picture? I mean, you've got it here. I don't need to bring it up, right, Mathematica? Okay. All right, now let's talk about the type 2 regions. Now, I actually do need to bring up my notes. 12.2. Okay, so here's the type 2 region. The difference between the type 1 region and type 2 region is that your y's are trapped between two constants, and this time your x's are trapped between two functions of y. So hopefully in Cal 1 you saw this, where you had functions of x could create this region, or you could kind of turn everything sideways, and these two functions, the red one here and the blue one here, they pass the vertical line test, but horizontally. It's kind of weird. When you say function of y, you look at this and you go, does that pass vertical line test? That's what you do. When you have a function like the type 1 region, right, up like this, you go vertical line test is this way. But when they're functions of y, you have to turn your head and ask the same thing. So I don't want you to call it the horizontal line test, because it's not the horizontal line test. Horizontal line test is how you test to see if a function has an inverse. So it's not the same thing. So you turn this way, you look at lines that go through here, and it cannot hit them more than one time. Can you look at the blue and the red here as functions of x? No, because look at the blue one. If I draw a line right through here, it hits it in two places, so it fails to be a function of x. So when you have that happen, when you have something that fails to be a function of x, you instead look at it as a function of y. Hopefully it'll work out that way, and then it turns into a type 2 region. As far as the integral is concerned, though, the setup's almost exactly the same. Our y's are trapped between two constants. Our x's are between two functions of y. And therefore, the double integral of some function f of x over that region D, it just switches, doesn't it? Look in here. Do y'all see my typo? Do you see that? That's typo. aren't those h's functions of y, not x? Did y'all see that right there? Make sure you change that. Why do you think we call them h instead of g? Just to kind of distinguish it from the type 1. For type 1, we use G1, G2. Type 2, we're using H1, H2. So when we do this, the first thing we're going to do is integrate with respect to what? X, and then after that with respect to Y. So things got flipped over here. And then I added that, if you look at this, we've always been looking at a surface and everything below it to the ground. If you look at it as two surfaces and you're trying to find the volume between them, then you get this picture right here. So here's the ground. Our y-axis is here, so our y is trapped between C and D. This is our x-axis. So our x values are trapped between two functions of y. And then above it, you've got a G surface and an F surface. So the volume would be the difference between those two integrals. So subtracting G from F. All right, so here's the example. I'm going to get to the notes. I'll come back to this. Again, I'm going to act like I don't know what it looks like. So we're trying to find the double integral over D of XA dA on the region bounded by y equals x minus 1 and y squared equals 2x plus 6. So I'm going to start with the region first. I'm going to try and draw the D. Y equals x plus 1 is a line, right? Has a y-intercept of 1. Yes? Negative 1, I mean. Right, negative 1. So if I come down here, call that negative 1, put a dot here, I've got that. And then it has a slope of 1, so I go up 1 over 1, up 1 over 1. So I've got something like this, up 1 over 1. Another point here, and then I could draw a straight line through those. And I will say this is y equals x minus 1. I'm not going to call it G1 or G2 right now. I'm not going to call it H1 or H2 because I don't know yet what type of region I have. Now I go to y squared equals 2x plus 6. If I try and solve this right now for y, I have to take the square root on both sides, don't I? And when I do that, I have to do plus or minus. And when I do plus or minus, I actually create two functions. One of them is a reflection of the other over the x-axis, which means it would fail the vertical line test, our traditional vertical line test. So it's not possible to determine y as a function of x. However, you can determine x as a function of y because you can solve this for x. Y'all see that? So let's solve that for x. I'm scrapping this. And I get y squared minus 6 equals 2x, which means that x equals 1/2 y squared minus 3. And that's a parabola in y, though, right? It's a quadratic in y, which means that the parabola opens up sideways instead of up and down. Because the number in front of y squared is a positive number, it opens to the right, not to the left. And the fact that I have negative 3 here means that it actually moves which way? To the left 3 places. So it's kind of like the up-down, this thing from our normal parabola, but now everything's left and right, positive being to the right. Now, I can tell you right now, just by looking at this, I'm not quite sure where they intersect each other. I'm not exactly, just by looking, I don't know where they hit. So I'm going to try and figure out where they hit each other right now before I draw my picture. So to do that, I solved this one for x, right? This equation, I solved it for x. I'm going to solve that one for x real quick and set them equal to each other. So if I take the one up here, solve it for x, you'll get x equals y plus 1, right? Now set those two x's, y plus 1 equal to this. So y plus 1 equals 1/2 y squared minus 3. How do you do that? Quadratic formula, right? Now I'm going to try and clean it up first. I move everything to one side. 1/2 y squared minus y, minus 4 equals 0? So I just moved everything to one side. And now I don't like fractions, so I'm going to get rid of the 1/2 by multiplying by 2. Right? Multiply both sides of the equation by 2. And now that's factorable. Y minus 4, y plus 2 equals 0. Set each factor equal to 0. You get y is 4, y is negative 2. Right? Now those are y-intercepts, right? Not x-intercepts. Or not intercepts. Those are my y points. That's the y values where I hit, right? So how am I going to determine these as points? I go back and get x, right? So here's how we can do this. Watch. I know that when y is 4 and y is negative 2, these two graphs hit each other. So all I have to determine is what is x if y is 4. Which one of these equations can you use? Either one. I like how that thing does that over there. Just sits there. It's really annoying. So I can do an either one, and it should give me the same answer, right? Because it's where they hit each other. So I go with the easier one. If y is 4, x is what? Yeah, right. Into the first one right here. If y is 4, x is 5. So that means 5 here. And if y is negative 2, x is what? Negative 1. So when I go to my graph, I can actually now take these points and use them, right? So where is 5, 4 going to be? Shit, I drew my graph too small, didn't I? It was a pretty good looking graph, but now I'm realizing that I have to go out 3, 2, 3, 4. So it's off my picture, right? No worries. That's why I have an eraser. Let's start my graph over. I know I've got to go out 1, 2, 3, 4, 5. I've got to go out 1, 2, 3, 4. I know right now that they hit here. And I also know that they hit at negative 1, negative 2. I know they hit here. Those are my points where I intersect. Now let me put that line back in. That line that we had, it had an x-intercept of negative 1, and it has slope of 1. Ooh. All right. Oh, come on. You can do it. You can do it. Chet, get back there. Okay, there we go. Right? My line's got to go through those 2 points because that's where they hit each other. And then that parabola, remember that parabola had to start out at negative 3 on the y-axis? So it had to go like this and open up sideways. I don't really care about how it opens up or where it hits anywhere. All I care about is that they hit each other there. See, what I'm saying is I'm kind of waving my hands to the x-intercepts. I could give a shit. I mean, y-intercepts. I don't care where they are because they're not relevant to any of this, right? So my picture's not perfect here. And now we have our region. Ah, what happened? Come back. We have our region right here. We look at it. It's a type 2, right? It's a type 2 because my x values are stuck between, I'm not going to highlight it. My x values are stuck between 2 functions of y, and my y values are stuck between 2 constants. Are you comfortable with understanding the difference between type 1 and type 2? Why you cannot look at this as type 1? Why can't you look at it as type 1? You got a function on top and a function on bottom. Yeah, what happens right here? Right there. Look at that little blue piece right there. Which one's on top? The blue. Which one's on bottom? The blue. So it's the same on top and bottom, which means that when you subtract, you get 0. So it's not a function. Right there in that little region, it's not a function of x. But if you look at it the other way, it works no matter what. The red is always, see, when we turn our heads, the red's on top of the left, or on top of the blue. All right, let's label some of these points. Where was, how high up did we go? 4? So our y-axis here, we go up to 4. And how far down do we go? Where is this point? -2? So our y values are between -2 and 4, and our x values are between these two functions of y. Now, the blue one, let's label that h1 or h2? The blue one. h1 of y, and it's going to be the parabola, which was 1/2 y squared minus 3. And the red one will be h2 of y, which is what was it? When you say h2 of y, that means it's a function of y, right? Which means you had to have solved for x here. So what goes here? What is it? You can't put x minus 1 because now it's a function of x, right? It depends on x. It's got to be the y plus 1. It's got to be that yellow one you solved for earlier, right there. See, x here is a function of y. So on your test that you're going to have, right? On your test, a lot of these problems that you'll see, it's going to be set up the integral, do not evaluate. And what I'll be looking for is a good picture. Okay? A good picture. I want to see things drawn out, labeled, everything, all the algebra done to solve the intersection points, all that work, set the integral up, proceed on to the next problem. Because once it's to the integral, at that point it's really kind of trivial, you know. It's the setting up of the integral that's important. I think we have everything we need, right? What's our double integral? The first limits of integration are restrictions on y, which are -2 to 4, right? Now the integration limits of integration are going to be our functions of y, our h1 and our h2. h1 was 1/2 y squared minus 3, right? And the other one was y plus 1. What are we integrating? What's the function we're going to integrate here? xy. And now we're going to go dx dy. Equals ... which I won't do. What's the antiderivative of that? The inner integral, what's the antiderivative? 1/2 x squared y, right? 1/2 x squared y. And you'll be replacing what's with what? You're replacing the x with those two things. So just make sure you get everything in order there. You know, make sure you understand what's being replaced. Any questions? Let's look at example 4. Find the volume of the tetrahedron bounded by x plus 2y plus z equals 2, x equals 2y, x equals 0, z equals 0. Tetrahedron? Tetra meaning how many sides are there to a tetrahedron? What does a tetrahedron look like? Something like that. That's an example. What's important in this problem, okay, is that they don't give you the simple integral, and here's your region bounded by. That's completely up to you to determine, okay? So let's talk about what we're given. We are given 1, 2, 3, 4 equations, right? We're in three-dimensional space. The first equation is the equation of a what? Drum roll. What's that the equation? A plane. What is the direction of the normal vector of that plane? 1, 2, 1. Right? Has nothing to do with this problem. Just making sure we all understand that's a plane. And because we have the equation of a plane, we know what the normal vector is, right? That's the one thing the equation of a plane gives us that we like. All right, what is this? X equals 2y. In 2D, it's a line. 3D, it's a plane also. What's the normal vector of this plane? 1, -2, 0. Or -1, 2, 0. Or any scalar multiple of that. Okay, what is x equals 0? It's the YZ plane. Its normal vector is 1, 0, 0. And then here, XY plane. So we have a plane, we have 4 planes, don't we? They all come together, and they enclose a region. And we want the volume of that. So let's start, I suppose, with the region itself, right? Let's try and get the region. So what I'm looking at here is on the ground, on the XY plane, the domain. If I'm looking at the ground, what's Z? If I'm looking at just on the ground, if I'm looking in the XY plane, what's Z? Z is 0. I'm going to keep that in mind this whole time. Z is 0 as I look to the ground. So let's talk about that first equation when Z is 0. If Z is 0, what does that first equation become? X plus 2y equals 2, which means y equals -1/2 x plus 1. What did I do there? Just solved here for y, didn't I? Move the x over, divided by 2. And that's the equation of a line, because we're looking in this xy plane. That's the equation of a line. Can you graph it? Yes, you start with the y-intercept of 1, and then you, from there, move slope down 1, right 2. And I draw a line. Drawing that line is something that I covered in my, like this problem right here, x plus 2y equals 2, is a problem that I covered in my 0310 class, which is a developmental class. And it's very difficult to explain to them why that would be useful. But it's just part of, I mean, that's like a test question in 0310, right? It's like a test question. So in here, we use it, but it's almost just like this subtle underthought for us, right? It's not even worthy of a test. But I guess what I'm saying is that you're always trying to find value in the math. Like, why are you learning to graph a line? Well, because later on you need to, and then you may be asking me, well, why do you need the volume of tetrahedron? Well, maybe later on another problem you need it. So it all is just building upon itself. And yeah. Okay, so here we go. We've got one line. What else can we do up here? Let's take a look at the x equals 2y. Nothing happens to that, right, when z is 0? But I can still look at that as a line. X equals 2y is the same as y equals 1/2 x. Can you graph this line? What's the y-intercept of that? 0. Then slope, up 1 over 2. So I go y-intercept of 0. I go up 1 over 2. I draw a line. Whoa. Pretty good. That worked out. What's that? Are they? You tell me. Are these slopes negative reciprocals? No. So they're not. If this slope would have to be what in order for those to be orthogonal? 2. All right, now we don't have a region yet, right? I mean, we have like 1, 2, 3, 4 regions, but nothing that's enclosed by everything yet. So now let's bring in the last 2 things we had, which was what? X is 0. Where's X 0? It's just the what? The y-axis, right? So I bring that into play. Should we start labeling some of these? This one was y equals half x. This one up here, this one was y equals negative. Oh, no, I got them backwards there, didn't I? Yep, I got them backwards. This one is negative 1/2 x plus 1. And then the one up here was 1/2 x. And now x equals 0 is what I'm going for next, which you said was the y-axis. Kind of exaggerating that. X equals 0. And then z equals 0. It's already shown. Like, that's what we assumed to get all of this to work out, right? Do you see the region enclosed by all these? It's right there. It's a little like triangular region, isn't it? Do you see how this is really just like the setup of it? It's not necessarily the integration itself. All right, so I obviously from looking at this say, you know what, that picture kind of sucks, but I'm going to need to know where these two hit each other, right? Because I kind of know a restriction on y here, right? It looks like y is between 0 and 1, but I don't know this right now. Like, what is a restriction on x? So I'd like to know that point of intersection, which means I need to take these 2 lines and set them equal to each other. Shall we? Sure. Take those, set them equal to each other. You get 1/2 x equals negative 1/2 x plus 1. Let's say we add half x to both sides. You get x is what? 1. And if x is 1, what's y? What's y? If x is 1? 1/2. So I'm basically saying that that point right there has an x-coordinate of 1 and a y-coordinate of 1/2. To me, this is all scratch work, okay? When I'm doing this, this is all just the scratch work of the problem. I'm ready to now draw a picture that's ready for presentation to my boss or whoever it is, right? You know, you go get a job, real-world engineer, and you work out a problem, and you don't get all your scrappy ideas on a piece of paper and throw it to your to the team, right? You organize it, you make it look good, you make it so people can read it. And that's what I'm going to do. So I'm going to put it together now. I know that they're going to hit. Here's 1. Here's 1 up here. This is halfway. I know that's a point. I know these are my 3 points there. That. I can label these. Now, maybe I should talk a little bit about what type region this is. What do you think this is perfectly suited for? Type 1 or 2? If it's type 1, then if I draw a vertical line, I've got to be stuck between 2 functions all the time. So let me see. If I draw a line like this, am I stuck between 2 functions? Right? Anywhere I draw a vertical line, I'm always stuck between 2 functions. It's those 2 lines, right? But what if I draw it the other way? So if I draw this one, let's say here to here, am I stuck between 2 functions? Yes, this line is a function of y, and then the ground here is a function of y. It's x equals 0. I said function of, yeah, function of y. So But will that always work? What happens here? At that peak, what's going to happen? You're going to have to change your function. So you could do this as a type 2, but you would have to do it as two separate integrals. One integral would take care of this, and the other integral would take care of this. Do you see that? But if we do type 1, it's going to be the same integral the whole time. Do you see that? So which one do you do? Either one. I'm going to go the path of least resistance here. I'm going to try and do type 1 region, up and down. So I draw my little up down here. This is then G2 of X. This one is G1 of X. And what were those? Those were those lines, right? So -1/2 X plus 1, and this one was 1/2 X. What's my restriction on X? Between 0 and 1. And now I just set up the integral, right? Well, we also weren't given the function, were we? Like, what are we supposed to integrate? That's just the ground, right? We said in the original problem we got 4 planes coming together. This is the region between them. This is actually the ground, z equals 0, isn't it? So the solid that we're looking for is the part that's above it. But what's bounding that top part? A plane. Which plane? Because we have 4 of them. Which of those planes is bounding us on top? The x plus 2y plus z equals 2. Why? Well, because this plane is the same as the yz plane, so it's like a wall on the side. This one right here, z equals 0, is the xy plane, so it's the floor. This one doesn't have a z in it, right? So z is free. So that's that, which one is it? X is 2y. That's this one right here. That's a plane that comes straight up out of the page, goes straight up and down, cuts through. So we got these 3. So the only one left is this one, which is going to give us our the top, the cap. Y'all okay with that? Now I'm going to do a pretty good attempt at trying to draw this 3-dimensionally. Watch this. Let me draw that plane. The plane was x plus 2y plus z equals 2. I know you're probably sitting there saying, do I really need all this detail? As we progress through this chapter, you'll see that we've got to get pretty good grasp of drawing things 3-dimensionally and getting those regions in order. So I'm intentionally showing you as much as I can here. How could you graph this plane real quickly? How could I graph it? How many points do you need, for a plane? 3? How about an x-intercept, a y-intercept, and a z-intercept? Where does this graph hit the x-axis? How would you figure that out? Set y and z to 0. So set y and z to 0, and you get what? 2? 0, 0? So this is x, this is y. So I'd be here. How about a y-intercept? Set x and z to 0, you get y is what? 1. So that'd be here. And how do you get the z-intercept? Set x and y to 0, you get z is 2. Okay? Now imagine connecting those points like this. Do you see that that's a plane? That's where the plane hits the 3 axes? Yes? Now the floor of this, right, is z equals 0. Where is our region in this picture? Wasn't it this piece right here? Was that it right there? On the ground? Go back up here. Where did this line come from right here? Where did that come from? Didn't that come from that x plus 2y plus z equals 2, and we had set z equal to 0. So that's the actual plane that has the angle on it. That's where it hits the z equals 0. That's this part. And then that other part right here, the greenish part there, is this one. And then, of course, x equals 0 is the backside. All right, let's get the integral. I just wanted to draw a little bit of what's happening here. The integral would go, let's see, we're going restrictions. The x's are between constants, so it's between where and where? 0 to 1. Our g1 of x was 1/2 x. g2 was negative 1/2 x plus 1. And now what is the function we are going to integrate? It must be a function of x and y, shouldn't it? So what we know it's that top piece, that plane, right? So what you need to do is take that plane equation, which was x plus 2y plus z equals 2, and solve it for z, right? Solve that thing for z. And that'll be 2 minus x minus 2y. So if you solve that, you get z equals 2 minus x minus 2y, which means f of xy equals 2 minus x minus 2y. And that's what goes in here. And we will integrate with respect to y first, then x. There's your integral. Question? Here it is. So there's that ground. There's that region we just found on the ground. There's our solid right there. See the plane? That blue thing is our plane that came through there. Make sense? But we're looking just at, from the top. There it is. Ooh, this is a great problem right here. So you have this in your notes. So I'm just going to go straight to me doing this. We are trying to find integral from 0 to 1, integral x to 1 sine y squared dy dx. So check this out. If I do this problem right now and I say, all right, just evaluate the double integral, right? Evaluate it. The first thing you'd have to do is find the antiderivative of sine of y squared with respect to y. Right? Mathematica. Integrate sine y squared, right? Ooh, I forgot a bracket. Sine y squared with respect to y, please. Oh, it's a Frenzel function, of course. Yeah, so this is like a Frenzel function is basically a way of computing it within some sort of error. So it's basically, this is telling us right now, you're not going to be able to integrate that. It's kind of like the classic one from Cal 2, the e to the negative x squared problem, that you can't integrate unless you can do power series, then you can do an approximation. So this is not integrable, right? According, if we believe Mathematica. However, let's see what we can recover from this, from the double integral itself. Because dx is on the outside, we know that the restriction on x is what? Between 0 and 1? Watch me start drawing this. I know my x is between 0 and 1, right? That's what I know. And I know that since y is the second, or on the inner integral, I know that this 1 and the x here, that those are actually my g1 of x, right? And I know that this is my g2 of x. Why am I not saying h? Because this is a type 1 region, right? Type 1s are your x is between two constants. Your y is between two functions. So I can actually draw those over here, can't I? G1 is the one on the bottom. What does x look like? What does y equals x look like? It's just a diagonal, perfect diagonal. Looks like that. I think I'm way off on that. That would be G1 of x. G1 of x equals x. Now, what does G2x look like? G2 of x. It's 1. It's the horizontal line that passes through 1. So it would look like this. So that's G2 of x. Right? And so it makes perfect sense that that right there is a type 1 region, isn't it? But it is also a type 2 region, isn't it? So instead of looking at it as a type 1, let's attempt to look at it as a type 2. If we look at a type 2, then we have to be stuck between these two, right? Here and here. And these need to be functions of what instead? Functions of y instead. So can anyone tell me what this bottom piece is here? That's x equals 0, right? So I can just say h1 of y is 0. So no matter where you are, it's always going to spit out 0. How about this one up here? It's y equals x, right? But I need to solve it for x. So x is y, right? So this is just y. Do you all understand that? Yes? Y and 0. So I should be able to reset this double integral up using it as a type 2 instead of a type 1. And let's see if that does anything for us. What's our restriction on y? 0 to 1 still. What's our restriction on x? Our x is stuck between these two, right? 0 to what? Y. So you may be looking at this and comparing it to your other integral up there, and you say, oh, I went from 0 to 1. Well, I was going from 0 to 1. Here's 0 to y. This one was x to 1. So big deal. What are you gaining? Well, do you see what you're going to gain? Yeah, look at the inside. What are you going to integrate? What's the order? Dx, dy instead. And now, when you try and integrate this, sine y squared is a constant. And so you integrate it with respect to x. What's the antiderivative of sine y squared with respect to x? Sine y squared x. So I get sine y squared times x. I'm going to evaluate that from where to where? From what is 0 and y? From x equals 0 to x equals y. So let's plug these in. I forgot my dy on the end here. I'm going to do this one. If x is y, what do you get? Y sine y squared? So integral 0 to 1. Inside there, I'm going to get y sine y squared. And then minus, what do you get when you plug in 0? 0. So that's not even there. And so that's just basically that with respect to y. And that's really nice because this is just now a basic substitution problem, right? U is y squared. Du is, well, pretty close to that. Do you see that can be done? Just a basic technique. Just in case you forgot Cal 2, let's do it real quick. U is y squared. Du is 2y dy. So du is, so half of du is equal to y dy. That's the basic substitution. But this turns out to be 1/2 sine y squared, evaluated from 0 to 1. Pardon? Hold on. We still need to take the antiderivative. Negative 1/2 cosine. Jump the gun there. Let's just double check that. What's the derivative of cosine of something? Negative sign, that goes away. Derivative of what's inside is 2y. Oh, my y, that's what you're saying. Yes, y over 2. Then you plug in 1, you plug in 0. This part really doesn't even matter. I don't even care if I'm right or wrong here. Huh? Yeah, that's, you know what, let's just say this. I don't really care about this at all, okay? I don't even feel like thinking about that right now, okay? The point is, you can do this now with a basic substitution. And when you couldn't do it the other way. And that shows you some of the advantages of being able to manipulate a double integral. There are problems that you'll have for homework that says, change the order of integration. This is what they mean. You start with this double integral dy dx. If you're asked to change the order of integration, that doesn't mean you just go, oh, I just put dx dy and don't change anything else. That means you have to go and look at what does the double integral tell you about the region. That double integral, believe it or not, should tell you this picture, right? What's on those limits there? 0, 1, x1. That should allow you to draw a picture. All right. Any questions on that? Yeah. Frenzel, let's get him out of there. So that's why on this note, order might matter. Might make a difference on how easy that integral is. All right, this is just some more properties of double integrals. So we've talked about some of the properties. Here's some more. If you have a region D, and you can look at D as being the union of two smaller regions, but they have to be such that D is equal to the union of the two. Then you can just figure out the integral, double integral over D by adding up the double integrals on each of the regions. So it's kind of like on back in Cal 2, if you want to integrate from A to B, you can go from A to some point between them, figure out what that is, and then go from that point on and add those two together. If 1/2 was, yeah, I mean, you could. It would depend on what your D looked like, but yes. All right, this is a nice one. The double integral as the area of D. This is somewhat interesting, but check this out. I'll try and give you a quick little geometric explanation of what's happening. Let's say that on the ground I have a box, okay, like this. That's my D. And I want to know the area of that, okay, the area. Couldn't you also look at it this way? Here's the D on the ground. And if I find the volume underneath that's 1 unit high, so say that this height here is 1, okay? Then isn't the volume of that basically the length times width times height? And if the height is 1, then isn't that just length times width? So isn't that just area? Do y'all follow that? So by using 1, the height part of it does not contribute to it at all. So when we look at this formula right here, if we let the f of x, y, that's the thing we're going to integrate inside, just be that plane z equals 1, then what you're really doing is finding the area of the region you're integrating over. This is super powerful because when we get to triple integrals, you can actually find volumes of three-dimensional objects by triple integrating one. Okay, let's see how we can work this. Do I do an example? Let's say I please do. I don't. All right, well, I'm going to make one up anyway because this is a cool little application here. So let's try something that we like. Find area of ellipse. Ellipse. X squared over a squared plus y squared over b squared. What's the equation of an ellipse? You're talking ellipsoid, three-dimensional. I'm just talking about an ellipse. Equals 1. There's an ellipse, right? If A and B are, well, if A and B are 1 here, right? It's just basically the unit circle, right? Okay, so this is an ellipse. Now we know ellipses look like this, right? Like this. Well, centered at the origin. What's the area of it? Well, I'm sure it's in a book somewhere, right? It's in a book somewhere. How can you create it, that area, with the double integral? So let's take a look at this ellipse. This ellipse becomes our region, doesn't it? The question is, can you define it as a type 1 or a type 2 region? Well, why don't we do this? Why don't we just look at this first section over here? Whatever the area of that is, times 4 is our answer. Agreed? So can you come up with this region? Well, what's the x-intercept? What's the y-intercept? So where does this ellipse hit the x-axis? Well, that's when y is 0, right? Yes? What do you get if y is 0 here? You get x squared over a squared equals 1. Multiply both sides by a squared. Take the square root. So you get a or negative a, but negative a is on the other side, right? So do you all agree that that's a? How do you find this point? Well, this is the y-intercept, so you let x be 0. It's the same story. This time you solve and you'll have a b in there, so you get b up there. Yes? And then the origin is 0. Now, we can go about this two ways. We can look at this as a type 1 or type 2. Do you agree with that? Type 1 or type 2? I'm going to go with type 1. Why? I don't know. That's what I'm going to do. Now, what about this bottom function down here? We'll call it g1 of x. What is that? It's just y equals 0, right? Now, up here, g2 of x, how are we going to find that? Well, that's the actual ellipse, isn't it? So what I need to do is I need to get it as a function of x, which means I need to take this equation up here and solve it for y. So let me do that. Grab that guy over here. Let me solve this for y. Y squared over b squared equals 1 minus x squared over b squared. A squared, thank you. Then multiply both sides by b squared. Y squared equals b squared minus b squared over a squared x squared. Now, square root. And now I should have a plus or minus, right? But the plus is the positive one, right? The plus is the one on top. The negative is the one on bottom, which I'm going to throw out because I'm only looking in the first quadrant. So I have square root of b squared minus b squared over a squared, x squared. Can I clean that up at all? How about b squared? Can I factor b squared out of both? and then pull that out of the integral, the square root as a b? Because a and b are constants, right? I mean, keep that in mind here. So this is b, then what? 1 minus x squared over a squared? Okay, there you go. So back up to that g. g2 of x is b square root of 1 minus x squared over a squared. Do y'all follow this? Okay. I'm ready to set up the double integral that's going to give me the area of the entire ellipse. And here's what it looks like. It's 4. Why? It's 4 of those regions, and they're symmetric, right? Double integral of 1, right? Now let's talk about limits of integration. I was doing a type 1. What was the restriction on x? 0 to a. What is the restriction on y? 0 to b square root of 1 minus, or minus? Yeah, it was minus. X squared over a squared. dy dx, right? Because depending on what your region looks like, if it's type 1 or type 2 or a rectangle, that order of dx, dy doesn't matter. So they usually use dA for the general statement. What's the antiderivative of 1 with respect to y? Y. So we have 4 integral 0 to a bracket in here. We said it was y evaluated from what? Y equals 0 to y equals b square root of 1 minus x squared over a squared. And then dx. Now if you plug that in, right? Plug in y equals that into y. You get that b times square root, and then you plug in 0, you get 0. So you wind up having 4 times the integral from 0 to a of b square root 1 minus x squared over a squared dx. And since a and b are constants, you could, at this point, pull the b out of the integral, and then you could use like a formula, or you could use trig substitution or something on the integral with the square root, and then you could finish it out. Right? So this is reduced down to basically a Cal 1 problem. And just, pardon me? For the trig sub, here we have, you have to be careful with the formulas. They use a in the formula, like a squared minus u squared, or u squared plus a squared. Here, our u is 1, right? I mean, our a is 1. Don't mix it up with this a. So, yeah, 1 minus secant squared. Yeah, so secant. And you're going to have to address the fact that this is not just u, that there's a little bit of a scaling going on there because you're dividing by a squared, or by a squared. But I mean, at this point, it's Cal 1 or Cal 2 problem. Did I say Cal 1? I meant Cal 2. Let's just have a quick little integrate. What was it? It was 4 times b times the square root of 1 minus x squared over a squared. And we want to integrate with respect to x, right? And what were our limits of integration? 0 to a. 0, comma, a. I think my typesetting's wrong here. I'm probably going to get an error. Yeah. I need to put this in braces like that. AB pi. AB pi. Yeah. So what if this is the unit circle, right? If this is the unit circle, A and B are 1, you get pi, right? Well, what's the area of the unit circle? Pi r squared. The radius is 1, so it's pi. Am I making sense? So this is a more general formula than the pi r squared, I guess you could say. All right. That's just an application of the double integral. You can find the area. Now, in this problem, it turned out that we got down to a integral of a single variable, like a Cal 1 problem, but we could have actually set this problem up in Cal 1 without doing double integrals. It sometimes works out, though, better to do it in double integrals. Not necessarily now, because right now we have, unfortunately, only 3 types of regions. We have rectangles, we have type 1, type 2, but as we get into the next section, which is polar regions, then we start to see the power of using double integrals to get areas instead of what we've done in the past. Do we really want to do this one? 24 from the book. 28. I do want to do this one. Let's try 24 from the book. I don't think that matches up with the right problem. So let me see this. We're in 10 or 12.2. It's supposed to be number 24. Yeah, it looks good enough. We'll try it. Even if it's not the same problem, we'll try it. So we have, it says, find the volume of the solid. Okay, find volume. Of solid. Enclosed by z equals x squared plus 3y squared. And they also do say that that's a paraboloid. Okay, they tell you that's a paraboloid. And x equals 0, y equals 1, y equals x, and z equals 0. Z equals x squared plus 3y squared is a paraboloid. It's a bowl, okay? Kind of a weird bowl, but it is a bowl. X equals 0 is the yz plane. Y equals 1 is the xz plane moved out 1. Y equals x is the diagonal, but it's a plane. It's three-dimensional. Z is free, so it goes up and down. And then z equals 0 is the xy plane. Somehow all these objects come together, and we have a region enclosed by all of them. So I'm going to do my best to try and first come up with what's D, what's on the ground. So x is 0 is this, right? X is 0 is this. Y equals 1. Y equals x. And z equals 0 is the ground, isn't it? I can pretty clearly see 0, 1, that's happening at 1. So what type of region does this look like? Type 1 or 2, it's up to you, right? The question is, where's the paraboloid? Where's this? This is our surface, isn't it? This is kind of the thing sitting above it. So I want from that down, don't I? From this surface, z equals x squared plus y squared, down to this. So I'm going to integrate double integral of this function. That right side's my function, and I just need my boundaries here. So I'm going to do type 1. What's the restriction on x? 0, 1. What's the restriction on y? Careful. Our region is here, right? Where is our x? Where is our y stuck between? Well, 1's up here, right? This is x. So it's from x to 1, right? X to 1. This is g1 of x equals x. This up here is g2 of x equals 1. Do y'all see that? And I'm integrating x squared plus 3y squared. dy dx. That's it. Pretty straightforward integration on that one. I believe I have that. So there's the paraboloid. There's x equals 0. This is z equals 0, so there's the ground. This is y equals x. This is y equals 1. So if I look at all of this from above, let me try and do it. Can y'all see this our triangle right there? This is turned over, unfortunately. I'm not quite sure how that got so screwed up, but our region should be different, but it's this right here. Y'all see that? Now, let me redo this. Oh, man. Put all those back in there. And it looks like a big cluster there. So let's get the solid we're talking about is right there. I'm just going to pull everything out of here except the solid. So that's it right there. It's kind of tough to see that still. I'm still trying to look at it from the top. There we go. Kind of from the top you can see it. It's hard to see where the paraboloid cuts out of it. So, whatever. You get the idea? Yeah, this is right. Okay, let's look at number 28 from the book. So I'll just tell you what they are, what you're given. You're given here y squared plus z squared equals 4. You're given the planes x equals 2y. You're given x equals 0. You're given z equals 0. And then you're told you're in the first octant. All right, so again, the instructions here, find the volume of the solid that's bounded by this, and is in the first octant. That first octant we haven't had yet. Remember octants, the 8 octants? Okay. So let me try and get my head around what the D is, what the region on the ground looks like. What is y squared plus z squared equals 4? It's a circle in 2D, but in 3D it's a cylinder. And which way does the cylinder go? Along the x-axis. Remember, the variable that's missing is so it's a beer can spilled. It's laying there. It's just infinite beer can. It's laying down. It's just a tragedy, right? So wherever your x-axis is, it's going down that axis. Has a radius of 2, right? All the way around. Then you have x equals 2y, which is a line in 2D, but a plane in 3D. I'm going to try and do this with the xy like this, right? So I'll be able to draw that on here. That's y equals 1/2 x. So up 1/2. That's that one, right? Agreed? What about x is 0? Well, that's the y-axis like this. And z equals 0 is the ground, is the floor. So if you look at this right now, we have not enclosed a region, have we? We have not enclosed a region. What else do I have to consider then? That's right. If I'm on the ground, remember that z must be 0. If I'm looking on the ground, z is 0. And then look at that beer can, and what you have now is this. So y is what? Plus or minus 2, right? But I'm in the first octant, so y has to be positive 2. So y is 2 just so happens to be here. Well, and my picture is just kind of poor now, because these are supposed to hit each other, aren't they? Where would that line hit at 4? See, I have to figure out where those hit each other. You'll see that point of intersection is important to me now. They hit each other at 4. How do I determine that? You set this one, which is y equals 1/2 x, equal to what? This flat line 2. So you basically set 1/2 x equal to 2. Multiply both sides by 2, you get x is 4. Is that all right, everyone? Type 1 or type 2? Type 1. Okay, I like that idea. Could you do type 2? You could. I'm going to do type 1. My g1 of x is what? 1/2 x. My g2 of x is 2. My restriction on x is 0 to 4. Now, what's the cap here? I mean, what's the solid? It's the beer can, right? I've got a beer can going down the x-axis. Where's my x-axis? This way, right? So imagine, if you could, a beer can. What's the radius of that beer can? 2. So imagine a beer can superimposed here on top of this, right? I'm trying to get it three-dimensional on top. I'm looking at just the beer can above that region and looking at the volume down. And because I'm in octant 1, right, I'm only considering stuff to the positive x, positive y, and positive z, so the stuff straight up. So z equals 0 is the bottom, right, the floor? And they gave that to us, didn't they? Inside that beer can, above that triangle. It's important that it's above because they gave us z equals 0, right? That told us the xy plane, but they could have been asking for what's below it. But they said first octant, which meant that we had to be above. Okay, so let's set up the integral and then we'll take a picture. We'll take a look at what it is. 0 to 4, right? Restriction on x. Restriction on y. 1/2 x to 2. The function, the square root of 4. So where do we get the function? It's the beer can solved for z. So move your y squared over, take the square root, plus or minus, but you only have to consider the positive because we're above, we're in octant 1. So square root 4 minus y squared. D y dx. Can you integrate that with respect to y? Yes, there's probably a formula in the back of the book that's exactly a minus u squared. Like you don't even have to do trig sub. There's a formula for it. But it could be done. Then you plug in these two limits, then you integrate again. Not going to do it, but that's what it is. Here's the picture, maybe. Okay, so here is the cylinder. There's your beer can, okay? Going down the x-axis, so we all know which axis is x now, right? Here's the xz plane, so that was, no, sorry, the yz plane, so that's x equals 0, right? Was one of ours x equals 0? Yes, okay. Then here comes the xy plane, that's z equals 0, so there's the floor. Here's that diagonal plane. And so, I won't spin it, but we're talking about this in here, right? And if I put it in there and take everything else out, we're talking about that piece right there. What's this, the volume of that? Okay? Questions? Do I have a homework assignment here? I don't have a homework assignment. I gave you a homework assignment for the 12.1 and 12.2, right? I didn't give one for 12.2? Yeah. Oh, yeah, because we didn't really do a bunch of these. All right, so let me give you something for 12.2. We'll kind of cut out of here a little early today. Unless y'all want to start talking polar. You're good? Okay, so for 12.2, this is going to be page 707. Evaluate the double integral. Let's go 15. I like 17 because it's got a little triangle. You have to come up with the functions. 21, 25, 27. $31. Now, these problems are going to be change integration order now. 37, 39, 41. So be careful on 37, 39, 41. All it says, sketch the region of integration and change the order. That's all it says. It doesn't say evaluate. On all of these problems, everything that I've put up there for homework, you should take it all the way to the answer. Like you should take it and get to the numerical answer for the volume. But maybe as you're going through it, just set all the integrals up first, because that's the most important part. Then come back after that and go back through and find the actual volumes. All right, we start 12.3 on Wednesday. Have a good day.